Okay, so I believe it's we can actually start with the presentation. So welcome everybody. Today is the third lecture of the mini course on symbolic dynamics for non-uniformly hyperbolic systems. And today I will mostly focus on the construction, on the theorem of Sarig from 2013.
Uniformly hyperbolic systems.
I'm actually
today,
hearing some just a minute. Let me mute some people. Oh, okay. And so so today I will focus mostly on the construction of symbolic dynamics for non-uniformly hyperbolic diffeomorphisms. And as usual, we will focus on dimension 2 to easy the explanation of the main new ideas. So in the next lecture, I will explain to you how we adapt this technique, or will employ this technique for more difficult contexts, such as billiards and flows, and perhaps non-invertible dynamical systems. So I would like to start recalling to you what we did on the last lecture so that we can continue. So on the last lecture, we put here, we used what we had done in the first lecture about invariant manifolds for uniformly hyperbolic systems. And then we understood that if you want to do the same thing in the non-uniformly hyperbolic context, the crucial idea is to restrict ourselves to points that have some non-uniform hyperbolicity in which the parameter Q does not decrease to zero exponentially fast. So this gave rise to the subset NUH star, in which we could apply the graph transform technique and then obtain invariant manifolds for points or for trajectories that are inside this set. So we kind of completed the construction of invariant manifolds, both in the uniformly hyperbolic context, as well as in the non-uniformly hyperbolic one. And we also explained how to do it in more complicated situations, just like point array return maps of flows and billiard maps. So then we started discussing how to effectively construct Markov partitions. And on the last lecture, we focused only on the uniformly hyperbolic diffeomorphisms. So the idea was following Bowen's approach of pseudo-orbits. So the first thing that we did was to introduce pseudo-orbits for uniformly hyperbolic diffeomorphisms. And actually, we rephrased everything about pseudo-orbits in terms of this notion that I introduced called epsilon overlap. So you should recall that in the uniformly hyperbolic situation, saying that two Lyapunov charts do epsilon overlap is nothing but saying that their centers x and y are close enough. So this was a kind of overshooting on the point of view of notation, just to say that 2 points are close to each other. But today you will see that the notion that we introduced will be easier to understand what we will do today. So that was the reason that we represented pseudo-orbits by means of this new notion of epsilon overlap, because today we will do it for the non-uniformly hyperbolic context. So after introducing this notion, we understood that the context of graph transforms could also be applied not only to real trajectories, but actually to pseudo-orbits. So because of this, we were able to develop the method of Bowen, in which he constructed Markov partitions using graph transforms along pseudo-orbits. So recall that we divided the construction into 3 steps. The first one was just considering a sufficiently dense subset of our phase space. The second step was constructing an intermediate coding map, which was very good in most for most conditions that we wanted, but unfortunately was usually infinite to 1. Then the third step was to kind of pass from this infinite one to an actual finite one coding, and it was based on a Bowen-Sinai refinement. So every time we saw an intersection of rectangles, we divided the rectangles like this, understanding the stable and unstable manifolds in which parts of the rectangles do intersect the other one with respect to these stable and unstable manifolds. So this is the summary of the last lecture. So today, what we want to do is to be motivated by this construction that we did on the second lecture, and then construct Markov partitions for now the non-uniformly hyperbolic situation. And the usual difficulties that come into play are that, first of all, and I already told you that a few times in the previous lectures. So the objects that we consider, in particular passing charts, which are the usual charts that we allow ourselves to understand hyperbolicity in this context, they do not vary continuously. And this was actually very important for us in the uniformly hyperbolic situation, because whenever x was close to y, we knew automatically that all stable and unstable directions were close one to the other, and so the Lyapunov charts associated to these 2 points are close to each other. And now we lose continuity, we only have measurability. So in principle, we could have 2 nearby points very close in the manifold, for which the objects that we use to measure the hyperbolic feature of our points are very distinct one to the other. Okay. Actually, this is the second. The second difficulty is totally related to, and kind of explain the first one. Is exactly what I'm trying to tell you, which says that the non-uniformly hyperbolic behavior of points varies a lot. So quantitatively, this means that exactly the stable, unstable directions, and also the parameter Q that we introduced, there is no reason for 2 nearby points having these quantities close to each other. But fortunately, at least we know how to measure this non-uniformly hyperbolic behavior. So we have introduced a bunch of parameters that allow us to understand exactly this non-uniformly hyperbolic behavior of each point. Recall, S and U are parameters that measure how good the stable direction contracts. U measures how good the unstable direction contracts in the past. Alpha measures how distinct the stable and unstable directions are. So alpha is just the angle between these 2 directions. Recall, we are all the time focusing on the context of surface diffeomorphisms. That's why we only need one value to measure the hyperbolicity along the stable direction, which has dimension 1, one value to do that for the unstable direction, and then alpha is just an angle. Okay. Then, based on these 3 parameters, we introduced map C of x, for which it's the norm of its inverse is related to this parameter capital Q here, which says us to each scale we have to reduce our passing chart in order to regain the hyperbolicity along the trajectory of the point. Then we introduce 3 extra parameters which are directly related to the graph transforms. So the small q is in some sense measuring how fast the big Q is possibly converging to 0. So remember that the small q is an infimum of the big Qs along the trajectory of the point. So this is a good scale to apply graph transform methods. And we actually divided this definition into 2 parts. One that only sees the future behavior. This is the small qs. and the other one which only sees the backwards, the past behavior, that's the small qu. And we understood that we could actually consider the stable graph transform only with this scale, and the unstable graph transform only with this scale. And the good feature is that usually we could have QS bigger than small q, so that the stable manifold that we constructed was actually of this size, which was potentially larger than this size. So in some sense, and I told you on the last lecture, these two parameters are the largest scales in which I can consider stable graph transform and unstable graph transform. So we are doing everything in a kind of almost optimal way. Okay, so these are kind of the difficulties and the first input that we introduced in order to bypass these difficulties. And now I wanted to mention what are the previous results exactly on the question that we want to address. We want to construct Markov partitions for non-uniformly hyperbolic systems. What was known before the main result of Sarig that I will mention today? Well, something was known, and it was due to Catoc. It's a quite old and famous result from 1980, in which he constructed the now called Catoc horseshoes. So in the context of surface diffeomorphisms, what Catoc did was, if this surface diffeomorphism has positive topological entropy, then you can find actual horseshoes with finitely many legs. So finite, in the symbolic point of view, they have finitely many symbols, and to which the entropy of these horseshoes can be as close to the topological entropy of the diffeomorphism. So in some sense, you can approximate the full topological entropy of your surface diffeomorphism using genuine uniformly hyperbolic compact subsets, which are these horseshoes with finitely many symbols. And the idea of Catoc was exactly to do what? Well, the machinery of passing theory that constructed invariant manifolds was already present. So his idea was, okay, so what if I know that all these objects do not vary continuously, but I can restrict my attention to the passing sets. Passing sets are exactly subsets of your phase space in which all the quantifiers, they vary continuously. This is a sort of applying Losing's theorem. If you have something that's measurable, then it's basically continuous on sets of large measure. So you can restrict your attention to these large sets in which continuity holds, and once continuity holds, then you are in a good shape to apply exactly the notion of pseudo orbits. I think my internet is a little bit unstable. Are you hearing me?
Yeah.
Yes.
Okay, good. If for some reason you don't hear me, please let me know, because otherwise I will be speaking only to myself here. Okay. So the idea of Catoc was like that. Okay, things vary measurably, but on large sets, they vary continuously. So I restrict attention to these large sets and apply Bowen's approach using the notion of pseudo orbits. He indeed needs a more precise version of pseudo orbits. And if you look at the Catoc-Hasselblad book that has an appendix by himself, by Catoc and Mendoza, exactly this notion of pseudo orbit that's present there is the notion that allows himself to construct these horseshoes. Okay. So this was known since 1980. And well, the problem is that these horseshoes, they can have entropy as close to the topological entropy as we want, but not necessarily you can find one horseshoe with entropy exactly equal to the topological entropy. you can approximate, but maybe you cannot make it equal to. And this was exactly the new result of Sarig from 2013, at least it was published in 2013, in which he was able to construct this object, which I will still call horseshoe, that now has countably many symbols. So in some sense, it's a horseshoe with countably many legs, but that it has full topological entropy. So in some sense, you relax the assumption on the number of symbols passing from finite to countably many, but fortunately, under this relaxation, you are able to get the full topological entropy of the system. So this is a very satisfactory answer from the symbolic point of view in the terms of entropy theory, because you are able to construct this object, which is combinatorially easier to understand, and that has the full topological entropy of your original system. So our idea today is exactly to try to understand how to prove this result of Sarig. Okay? Do we have any questions so far? I don't want this mini course to be a monologue in which only I speak. So if you have questions, people that were asking questions last time, like Marisa, Lucas, Leandro, you are invited to also make the questions not only at the end of the lectures, but also during the lectures. So do you have any questions so far?
I might have missed something, but what do you mean by full topological entropy? It is a measure with maximal entropy? You talk about metrical, okay.
Yes, exactly. So we are able to we are able to get the measure of maximal entropy and get the coding of this measure for almost every point of this measure. Okay. Actually, what we do is that we will consider a subset, just like the NUH, and we will be able to code this whole subset. And we know that this subset, it carries all the entropy of the system. So we do not even need to talk about invariant measures. We can only restrict ourselves to this invariant subset that exhibits some sort of non-uniform hyperbolicity. Any other question?
Yuri.
Yes.
Why taking union of Catoc horseshoes is not a good idea? If you take the union of a sequence of Catoc horseshoes?
That is a good question.
Should we think about it?
I wouldn't be able to understand it, for instance, these Catoc horseshoes, they are not invariant, okay?
No, H horseshoe is invariant, no?
The passing sets, they are not invariant. So the objects that you construct, they are not invariant. That's what I recall.
Yeah, passing sets. Yeah, you're right. Passing sets are not invariant sets. So you find these Catoc horseshoes that are invariant by some Fn. In fact, some
yes. Yes.
They come back to them. Yes. Yes. So you take the orbit of this horseshoe, you find some invariant set, in fact.
And you could have many intersections, right, of these guys.
Exactly. I never thought about it. This is just for curiosity, but it seems that it is not just a naive thing to take the union of them. Maybe, as you said, they may have intersections with different horseshoes, and then you will not be able to find some coding, some
global thing. Exactly.
Global coding.
Yeah.
Yes.
Yeah. Because as I told you, it's very important that this coding is finite to one. Okay.
Exactly.
Or at most countable to one. Otherwise, you cannot relate invariant measures. And well, even though the result does not focus on invariant measures, for the purpose of applications, we do apply to them. So not having this finiteness to 1 is a bad thing. So we are always looking for finite 1 coding.
Okay.
Yuri,
Okay.
you told that in the Sarik result you can find a measure of maximum entropy in that ratio. So, but in the union of this ratio of Catoc, maybe you can not find this measure.
Yeah, it can only be realized as a supremo, but not as a maximum, right?
Yes.
Yes, another difficulty of taking only the union. Good. Thank you, Wilton. It's good to know that that people are paying attention. So I think now I can continue satisfactorily. Okay, so this is the kind of let's say the way of relating to Catoc, but what we actually construct is a Markov partition on a set that exhibits some good non-uniform hyperbolicity. So recall I introduced to you this set. We fixed a parameter chi and we looked at points with some non-uniform hyperbolicity. And later on, for the purpose of introducing graph transforms, we constructed a subset of it, which was for the point for which the capital Q does not converge exponentially fast to 0. So now I will introduce a new subset, an extra subset, which I will call this NUH sharp. So now we have an even newer non-uniformly hyperbolic locus. And the idea is introducing some recurrence to the set that we have so far. So how do we introduce this recurrence? So this is the set. We consider now only the points that for which you have some non-uniform hyperbolicity, for which your capital Q does not decrease exponentially fast to 0. So this means that the small q is positive along the orbit. And then we require that the small q in the future becomes far from 0 for along a subsequence, and the same thing for the past. So in some sense, what we have here is a subset which is somewhat related to a union of passing sets. So the union in some sense appears here. Why? Because you can see the set in which K is bounded for T from T as a sort of passing set. So asking the point to having this lim sup bigger than 0 in the future and in the past, it means that its trajectory is visiting a single passing set infinitely often in the future and in the past. So this is the kind of recurrence that we are adding to this subset here, for which we have not considered recurrence yet. And so this will be the good set in which we will be able to satisfactorily find a Markov partition from. Okay, so let me just recall to you what are the 3 subsets that we consider. So we first consider this one, for which we have the invariant directions ES and EU, and the rate to which those possible Lyapunov exponents are bounded from minus chi. They give us these finite parameters S and U. So here we are only looking at the non-uniform hyperbolicity. Then we added an extra condition to require that this small q is positive. So this means that you have a sub-exponential big Q. And now the new input is to introduce some recurrence to some passing sets, which in some sense, the iterates to which you return to this passing set, they are kind of Plis times. Okay, I believe this notion of Plis times is nice to see as it is, because it's used a lot in the non-uniformly hyperbolic context, and even in the context of Young towers and so on. So this is a relation that I believe that will appear also in the talks of Zé Alves. Well, actually, Zé Alves is an expert in using these Plis times to understand non-uniformly hyperbolic systems. Okay, so with the introduction of this notation, now I can say to you what is the theorem that we want to discuss today. So here is the theorem. Let me decrease this a little bit. So the theorem of Sarig considers C1 plus beta diffeomorphisms on surfaces, and given a parameter chi bigger than 0, he is able to construct a topological Markov shift. So this is a symbolic space with the left shift, and a Holder continuous coding map, just like we wanted in the first lecture. So this guy is an extension of the original guy. So this diagram commutes. And furthermore, the image of this subset is exactly NUH chi sharp. And actually, once you restrict to this subset sigma sharp, which I will tell you in a minute what it is, then this pi here is finite to 1. Okay? Let me just warn you of a few things. This is not the original result that Sarig proved. So this is the way that we see nowadays his theorem. And this equality was studied by one of his students, Ben Ovadia. So he was actually able to obtain this not only in dimension 2, but actually in any dimension. This is very important for some applications. So he was actually able to understand what would be the image of this subset here of your symbolic space. And just to complete the statement, what is the subset of your symbolic space? It is basically the symbolic counterpart of this sharp subset that we introduced. Recall that sigma is a space of sequences. So a sequence is in this sigma sharp if you see a same symbol infinitely often in the future and the same symbol infinitely often in the past. So in some sense, it is a kind of recurrence assumption as well. So this is a kind of counterpart, symbolic counterpart of this more complicated set NUH sharp. And
Yuri.
Yes?
Sorry, so this equation number 2, it depends on key on the right-hand side, but not on the left?
It depends, because this guy that we construct, we fixed this guy.
Okay.
So we fix chi, and then we find this topological Markov shift, and we find this coding for which all of this holds.
Okay, thank you.
Okay. So the original result of Sarig, it actually got only this inclusion here. Or actually not. Let me see if it's this one. Let me think. No, it's this one. Okay. Yeah. So getting the other direction, this one, yeah, it's actually hard because, well, you're gonna see, we don't know how to directly to control the parameters of the coded points. Yeah. Great. Well, even if you knew this, you could make some applications. But for the new applications, for example, that I already mentioned, the generalized hyperbolic SRB measures that Ben Ovadia constructs, it is important to get the other direction as well. But I will state Sarig's theorem like this because it's exactly this version that I want to comment on the proof. Okay. Okay, so again, you have your surface diffeomorphisms is a geometrical object, and you are interested in understanding the non-uniform hyperbolicity of it. So you fix a threshold to understand the non-uniform hyperbolicity, and then you look from this threshold to a subset of your manifold, which is a kind of the good subset in which you have a good non-uniform hyperbolicity with also some recurrence. And what we are able to do is to construct the symbolic object to which a subset of it falls inside this set of good non-uniform hyperbolicity, and actually the coding is finite to 1 on it. So if you restrict yourself only to the restriction of pi restricted to sigma sharp, then you have a map that is finite one from here to here. So all the dynamical properties that are happening in this set can be lifted to this set here, and we can understand, because this set is combinatorially much simpler to understand, what happens here, and then project down back to the original subset and conclude the dynamical properties of the objects that we were interested in the beginning. Okay, so this is the idea, and this is the reason that for many applications, having this surjectivity and finiteness to one only in this subset is enough for us. Because, for instance, in low dimension, measures of maximal entropy live here. This is one example of application. Okay. So,
excuse me, Yuri.
yes.
I'm sorry. The original pi, it is surjective.
It is surjective onto this guy.
Okay. But outside this guy, not necessarily.
Not necessarily.
Okay.
Yeah. And even not the original, we use the same pi. Okay.
Oh.
No, actually, we make a few changes, because the set that Sarig considers, the NUH chi, is slightly different from ours. He actually only considers points which have Lyapunov exponents.
Okay.
Okay. He's able to obtain surjectivity onto this subset here. He's able to obtain finiteness to one, but he's not able to understand what is the image of this guy.
Okay.
Okay. Okay. Okay, so we will not be able to prove this theorem only using the same ideas that we did for the uniformly hyperbolic situation, because things here do not vary continuously. So because of this, new ingredients have to be added to the proof. And I will focus on the 5 main ingredients that I believe are the key ideas in order to being able to prove this result.
I'm sorry, Yuri.
Yes.
Can I ask a question? So you mentioned something about measure of maximal entropy being included in the NUH chi, but for which chi?
For which chi? So if you get a measure of maximal entropy, you just get a chi smaller than h. And then if this measure is ergodic, then almost every Lyapunov exponent will be bigger than chi, because it will be bigger than or equal to h, right? You have the Ruelle inequality, which tells you that h mu greater than or equal to the Lyapunov, no, sorry, smaller than or equal to the Lyapunov exponent. So the Lyapunov exponent will be bigger than chi. Okay?
Okay, thank you.
So any chi is smaller than the, so if you want to understand the measure of maximal entropy, any chi is smaller than the topological entropy will do the job. Okay. So here are the 5 main ingredients that I want to discuss today. I want to discuss the notion of epsilon overlap in the non-uniformly hyperbolic situation. Recall, in the uniformly hyperbolic one, it was a tautology, the notation that we introduced. Because whenever x was close to y, psi x was close to psi y. So now I will add a condition in order to have, for passing charts, this property as well. This is the notion of epsilon overlap. And then comes a very important notion, which is this one of epsilon double charts. So we introduced, to analyze uniform hyperbolicity, passing charts. Passing charts will not be enough for our interest, because in some sense, passing charts, they are analyzing the behavior at the stable and unstable directions at the same scale. So the idea of these double charts is to introduce 2 different scales, one to analyze the behavior along the stable direction, another to analyze the behavior along the unstable direction. So in some sense, passing charts, they are single charts, and then we are going to pass to this notion of double charts, in which we can separate the study of the stable direction to the study of the unstable direction. Then we are going to discuss this notion of coarse graining, which is how to reduce the study from uncountably many charts that we have, that we need a priori to consider to understand all trajectories, to only countably many of them. So recall that in the uniformly hyperbolic situation, this coarse graining was very easy. We just needed to consider a finite, sufficiently dense subset of the manifold. So if you have your manifold here, if you have a sufficiently dense finite subset, then we can code all trajectories using the pseudo orbits generated by this finite set. So applying this technique to this non-uniform hyperbolic situation is the new input of coarse graining that I will discuss in a few minutes. Then more difficult questions come into play. The first one is this improvement lemma. I will not tell you what it is right now. It will be clear as we go in. And then the last one is the inverse theorem. The inverse theorem is exactly related to the following question. So we constructed our coding map. So to every pseudo orbit phi, we get a point in the manifold that is coded. And the idea of the inverse theorem, it's actually an inverse problem. So what can we say if we know X? What can we say about V? So in some sense, we are trying to understand the inverse image of X. So we are trying to understand the fibers of this coding map pi. And this is an important and necessary question in order to prove the finiteness to one here. We have to solve an inverse problem. So we have to prove an inverse theorem. Okay? So these are the 5 main ingredients that in some sense do not come into play in the uniformly hyperbolic situation, but that play a key role here in the non-uniformly hyperbolic one. Okay, so let's go. Let's discuss them. Epsilon overlap. So let me make a comparison. Again, epsilon overlap in the uniformly hyperbolic situation was very easy because whenever 2 points are nearby, their invariant directions are nearby. But now you can have in the non-uniformly hyperbolic context 2 points very close for which the splitting associated to them is very different. And the consequence in the point of view of those matrices that we introduced is that these matrices, so recall C of X comes from R2 to TXM and C of Y comes from R2 to TYM. So these are the matrices that allow us to diagonalize the derivative of the map. And if these splittings are very different in 2 nearby points, then C of X and C of Y are very different. For instance, if you subtract one from the other and you calculate its norm, this norm could be a priori very big. Why? Because they are defined by these splittings, and these splittings are very different. So how do we actually impose some condition in order to have these matrices close to each other? So this is exactly the notion of overlap, to which we will actually need to consider an extra object associated to passing charts. So passing charts, we consider psi x, but now we need to introduce an extra parameter, which is the parameter in which we see the passing chart. It's a kind of a scale for each passing chart. So to each parameter eta, I'm going to introduce this new object, psi x eta, which is just getting the original passing chart at x and restricting it to the scale eta. Why? Because the scale is one thing that we will be interested in controlling from now on. In the uniformly hyperbolic situation, scale was uniform because everything varied continuously. But now, even though we have two nearby points with similar splitting, the scales defined by them, for example, the capital Q, might be very different. So we have to adjust the scales to nearby scales as well in order to be able to define this notion of epsilon overlap. Okay, so epsilon overlap will actually be a property of two passing charts. We are going to say when two passing charts have an epsilon overlap. So it's not only a property of the centers of the charts, but also of their scales. And when do we say that two passing charts epsilon overlap? So consider two of them, one centered at x1 with scale eta 1, and the other one centered at x2 with scale eta 2. And we say that these two passing charts are epsilon overlapping. In some sense, they are allowing us to understand the hyperbolicity at more or less at the same place with the same scale, if the scales are comparable. So this notation here just means that this quotient is between e to the minus epsilon and e to the plus epsilon. So this quotient is very close to 1. And here is the more difficult assumption to hold, is that, observe, to have the epsilon overlap, we require that the centers of the charts are close to each other, but we also require that the matrices C of both points are very similar to each other, in the sense that this sum is smaller than this number, which is potentially very, very, very small. So this is a very strong assumption. If you want an epsilon overlap to hold, you should choose proper scales that are comparable, to which this sum here is smaller than the product of the scales to the 4th power. So the smaller the scales are, the stronger the condition of epsilon overlap becomes. So the closer the points have to be, and the more similar the matrices C have to be from both points. So this is a very strong assumption that not only occurs whenever you get two nearby points. You need to have more things close to each other associated to the points x1 and x2. So here is the picture. So not only the splittings have to be similar, but also, and I will not prove, but it is necessary, that the parameters S of x1 and x2 are also very similar. The parameters U of x1 and x2 are also very similar. And this is exactly the condition that whenever it is satisfied, we can understand a neighborhood of x1 and x2 using either this passing chart or this passing chart, because their images, they cover more or less the same region of the manifold, and also the distortion associated to them is almost nothing. So actually, one consequence of this definition is that if you consider the composition of psi x2 minus 1 with psi x1, this is very close to the identity. Okay? We use this in the uniformly hyperbolic situation, but in that situation, this was guaranteed only by requiring x2 being close to x1. Now, we need these stronger assumptions in order for this change of coordinates to be close to the identity. So this is in some sense saying that if you have epsilon overlap, it makes no difference if you consider this passing chart or this passing chart to analyze the manifold in the neighborhood of these points. And why is this good? Because once we understand how to change from one passing chart to the other, we can actually understand how to analyze F from changing from passing charts to others. So recall a theorem that I stated for the uniformly hyperbolic situation last time. This theorem of Sarig is exactly the same theorem in this non-uniformly hyperbolic context. Our idea is now to analyze F using two different passing charts, one at X and one at Y. And to do that, we require not only that f of x is close to y, but that you have a passing chart at f of x close to a passing chart at y. So if this occurs, then you can understand your map F using these two passing charts, psi x and psi y. And the conclusion is that you recover hyperbolicity, because this change of coordinates, this representation of F in these two passing charts, they are again a small perturbation of a hyperbolic matrix. The same hyperbolic matrix that we had before, plus an arrow term which is controlled in the C1 plus beta over 3 norm. So epsilon overlap allows us to recover the hyperbolicity that we want in order to analyze our non-uniformly hyperbolic system. Again, the proof of this is just observing that f of x, y is the composition like this. And we know that this guy is almost hyperbolic. And by the epsilon overlap assumption, this guy is going to be close to the identity. So the proof is the same, but now the assumption that we require is stronger to guarantee that that change of coordinates is close to the identity. Okay? Any questions?
I have a question. How can we guarantee the existence of these overlaps for two nearby points? Because it resembles a lot continuity, and these etas could possibly be very small, smaller than Q, for sure.
Yes.
So it seems hard.
Yes. So if we don't have overlap, then it's better, because then we don't have kind of duplicity in representation of our model. Okay, but invariably we will have to require overlaps. So you will see when we deal with the coarse graining. In the coarse graining, we will exactly pass from this uncountable space, which is the space of all trajectories, to a countable one, which is a space, reduced space of countably many passing charts, not passing charts, but epsilon passing charts, double charts, that on which we have overlaps that allow us to consider pseudo orbits that will code all points that we want. So in some sense, it is good when we have not many overlap, but we will require overlaps to occur because it's using the overlaps that we will pass from actual orbits, which are uncountably many, to pseudo orbits, which come from countably many objects. Did you understand?
More or less.
More or less. Okay, so yes, it will be complicated because nearby points, they might have not overlap, but we will get to it. Okay. Okay. Any other question?
Yuri.
Yes.
On the overlap condition, the exponent 4 is optimal, or?
No, it's not optimal. It's, I believe, a 3 or a 2 is sufficient. But then while you prove, you pass from this estimate to some you have to lose something. So for some calculations, the 4 becomes 3 in the middle of the proofs, and then the 3 becomes 2, and then the 2 becomes 1. So if you have a better way of applying the calculations in the proof, perhaps you could reduce this to 3 or to 2. So it's not optimal, but it's sufficient. Okay? And we can do it with any number bigger than 4. If you want to put a 10 over there, we are also able to do it. Of course, epsilon overlap will be harder to hold if you change 4 to 10. But still, the idea of the proof and the techniques can be adapted to changing 4 to 10. All right? It's just a number that's sufficient for the bunch of calculations that are done in the papers. Okay, let's continue. The next input is a very, very, very important one. It's exactly how to separate the analysis to the stable and the unstable directions in a different way. So this is the notion of epsilon double charts. So motivation is as follows. The uniformly hyperbolic situation, we have no problems with this because the angles associated to the splitting, they are uniformly bounded away from 0. But now in the non-uniformly hyperbolic situation, these angles, they could be as close to 0 as we want. And if this happens, it means that it is hard for you to measure the hyperbolicity of your system along both directions using the same scale, because the angle is small, so these two directions are almost indistinguishable one from the other. So the solution that Sarig gave was, okay, so instead of considering the same scale to analyze hyperbolicity along these two directions at the same time, I will consider two different scales, one for each direction. So this is the notion of epsilon double chart. So the idea, or nowadays the easier way to explain this, is recalling what we already introduced for points in the NUH star subset. Recall that NUH star is the set of points in which the small q is bigger than 0. The small q allows you to consider graph transforms. And then we said, okay, why don't we separate the definition of the small q into a small qs, which only considers the infimum for forward iterates, and the small qu, which only considers the infimum for negative iterates. And as I already told you, these introduce two different scales that the first one allows you to analyze the behavior along ES, and the second one along EU. So it looks like that the right object to understand these hyperbolicities separately is to consider the same passing charts centered at the same point X, but if you want to consider the stable graph transforms, you consider the scale of QS, and for the unstable graph transforms, you consider the scale for the QU. So this leads to the definition of epsilon double chart, which is this. This is the notation for an epsilon double chart. It is passing charts centered at X, and you put here two scales in which you can see this object as a pair of passing charts. The first passing chart is considered at the scale PS. So let me just fix this because this should be on top. Okay. And this is the passing chart centered at X, which we will analyze the behavior of ES. And the other one, in which we will analyze the behavior of EU, will be this passing chart at the scale PU. So from the definition, an epsilon double chart is just a pair of passing charts centered at the same point. But conceptually, what they will do is that they will allow us to analyze the behavior, hyperbolic behavior along ES separately from the hyperbolic behavior along EU. One parameter for each of these directions. Okay?
Yuri, PS and PU or QS and QU? What is the relations? I'm confused, sorry.
So here, to each X, you can consider anything as PS and PU.
Mm-hmm.
But X has an intrinsic kind of PS and PU,
Mm-hmm.
which is the QS of X and QU of X. So PS and PU, the natural candidates that you associate are exactly QS and QU of this point. They are the intrinsically defined parameters for the point. But because we are going to have to make some approximations, perhaps we might not be able to take QS of X and QU of X as the scales, and we need to change them a little bit.
So you have two parameters, family. Two parameters for your chart.
I have two candidates for putting this as these parameters, but since I need to pass from actual orbits to pseudo orbits, I need to make approximations of these parameters.
Good. Good.
Okay?
Thanks.
Yeah. Okay, so now, since I defined these charts, now I want to define when I can pass from one chart to another chart by the action of F. So we define this in the uniformly hyperbolic situation. Recall that we consider, let me put this in blue, we consider psi x going to psi y in the uniformly hyperbolic situation if you have the proper overlaps. So you have the overlap of f of x to y and of f minus 1 of y to x. If you had this, then you could make that change of coordinates but to analyze f using these two passing charts at x and at y. Now we will do the same thing, but now for this much more complicated object of epsilon double charts, which will be the one that we'll use for the non-uniformly hyperbolic context. So get two of them, get two of these objects. One is centered at x with two parameters, PS and PU. One is centered at y with two parameters, QS and QU. When can we, from this one, apply the dynamics and go to this one? So if this happens, we write an edge from V to W. So the conditions are, in some sense, they seem complicated, but let me explain to you and try to demystify them. So we require a bunch of conditions now, which are much stronger than when we had uniformly hyperbolic maps. The first two ones, they are related, similar to the previous ones of the uniformly hyperbolic situation. We require an epsilon overlap of the passing chart at f of x with the passing chart at y, and also an overlap of the passing chart at f minus 1 of y with the passing chart at x. The scales that we require are the minimum between these two parameters. So these two passing charts, they have to be epsilon overlapping with this very small scale, which is the minimum between QS and QU. Let me diminish this a little bit so that you see the notation here, okay? And the same thing for the pre-iteration of the passing chart at Y. So you get an overlap with this scale here, PS and PU. So the proximity of these two passing charts have to be very, very close, because that sum has to be smaller than PS, PU to the 4th power. Actually to the 8th power, because it has PS, the parameter here with the parameter here to the fourth power. Well, this is not enough for passing from one double charge to the other, because we also need a relation between the scales of one to the other. And this, in some sense, mimics the condition that we needed for the graph transforms to be defined. So recall that QS and QU of points, so we introduced the QS of X and QU of X, and we showed that these guys, they satisfy a recurrence condition. And the recurrence condition is exactly what we require for the PS, PU, QS, and QU here in the transition from one double chart to another. In some sense, this first equality, what does it say? It guarantees to us that we can define the stable graph transform. Why? Because if we start with an almost horizontal graph here, defined with this scale, then if we apply f minus 1, we expect it to grow more or less of the order of e to the chi. Then we are sure that it grows, it becomes at least of this size. Well, if we want to define a new graph now on V, we cannot go beyond the capital Q associated to V. So in some sense, we have to take the minimum of these two values, and then we are able to define this, the image of this almost horizontal graph as a new horizontal, almost horizontal graph with this scale PS. So this is giving a recursion between the QS and PS in order to guarantee that the stable graph transform is properly defined whenever you have an edge. And the same condition holds here for this equality that guarantees that the unstable graph transform is well defined.
Okay? Sorry, maybe you chose QS and QU. Is it a good notation here? I'm a bit confused because you define.
Yes, it's a bad
QS.
Notation.
Yeah,
it's a bad notation.
But I don't know what will be the substitute. Maybe prime or something else. Okay.
Here I should put QS of X and QU of X. Okay.
Sorry,
Yuri, that they are of a point.
In the left side, it is PS equal to my minimum of and below QU, is it correct? No. Oh yeah. Okay. I see.
Yes.
No. Okay.
Because
Okay.
you go from X to Y.
I see. Okay. Thank you.
So the stable, you start here and you go here. So PS depends on QS, but they stable, unstable, you start here and you go here. So QU depends on PU.
Yes. Okay. Thank you.
So Yuri,
yes.
Excuse me. So if you have a pseudo orbit, so the parameters of the pseudo orbit are going to be like determined only by the value of two parameters, like these scales. You only have to choose two scales and then you can determine everything else or something like that. Because I see like PS, because it seems like PS is totally determined by QS.
Yes. So from QS, you can go to the past to define the stable ones. Yeah, you're right. And then QU, yes, if you have one guy here, you determine this one. But if you want to determine everything, you have to know the stable parameters for far futures. If you only know the zero of parameters, you can define the PSs for the negative values. So you can, because you can come back.
Okay.
Yeah.
Okay. I think I see. Okay. Thank you.
And the QU, if you know one, you know everything in the future they use. That's true. But how to know these ones? So you have to know something about the far past.
Yeah.
Okay. This is interesting because the recurrence condition is in some sense, that's what is allowing us to determine this, because the recurrence condition is telling us that you, in the far past, you return to a same kind of passing set. So at least you are bounded from 0 in the far past. So you can iteratively define everything in the future from the far past. Okay?
Okay. See, so how like this recurrence condition allows you to control the value of these parameters? I don't know, like just guessing.
Yes, exactly. It allows you you should see it as follows. We introduce the intrinsic values candidates for points, and they do satisfy this.
Yeah.
And now we relax this condition. We relax this assumption by now taking values which are not necessarily the ones we introduced, but still satisfying the same recurrence conditions.
Okay.
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 So we require the same conditions, but you be relaxed in the sense that these values are not necessarily these values. And in some cases, they will not be, because we will have, in some sense, to pass to approximations. And if you need to pass to approximations, we will not consider these values, but yet approximations of them, which will be the purpose of these values. Okay?
Yuri?
Yes?
So may I ask something? My question is kind of naive because I'm confused with the many objects which are lying around.
Yeah,
so,
yeah, that you are absolutely right.
So when we write this edge, like V edge W with an epsilon on top of the arrow, we are actually fixing 1, 2, 3, 4, 5, 6, 7 things to write the edge, right? The X, the epsilon, the PS, PU, QS, QU, epsilon.
Yes, so epsilon is fixed hence and for all. Okay. So you are fixing 6 things.
Okay. So my question becomes similar to what Marisa asked, I think. So epsilon is fixed.
Yeah.
It can happen that there is no choice for the other 6 arguments in order to write such an arrow. Or, I mean, trivially, if we take X to be X and Y to be f of X, I think. I mean,
and you take these guys here.
Yes, let's say the canonical choices for the indexes. Okay, we can fulfill the and write the error. But if we are not working with 2 points in the same orbit, it can be that we won't be able to write the error.
Exactly. Yeah. This seems too much to ask for. And it makes, and it might be a so strong condition that you are right. So if you don't get an original trajectory, this definition might be an empty one. But, and you have to have just faith now, because I'm not explaining to you the details now. This condition, even though it is very strong, it is still loose enough in order to have many edges.
Okay.
Okay. This is what I will actually say next about when we talk about, let me go here, about the coarse graining. The coarse graining will exactly be the theorem or the result for which we will pass to only a countable family of these objects for which all edges that we consider will be enough to shadow all points that we are interested in. This is a kind of a miracle. Because even though this condition of transition is very, very strong, it is still loose enough in order to pass to a countable family of these objects for which the pseudo orbits will cover everything that we are interested in.
Okay, I see. Thank you.
Welcome. This is actually much. So I have an ongoing, and I don't know for how long it will take because the pandemic complicated our plans, ongoing project in which we want to do something related to flows for this. And we had a definition for edge, which was, as you are saying, too strong to be true in general. So we had to redo the definition, making it more relaxed, so that with this new definition, we were able to get non-trivial edges. Okay. But let's say that we have edges. Whenever we have edges, then I can pass to the notion of generalized pseudo-orbit, which I will call epsilon GPO, epsilon generalized pseudo-orbit. What is it? It is a sequence of edges. So it is a path on a graph. So it is a sequence of epsilon double charts, such that from the epsilon double chart at position n, you have an edge to the epsilon double chart at position n+1. Okay? And as you are saying, this could not exist for non-truly orbits. Well, at least it exists for truly orbits. You see, if you get a point in the non-uniformly hyperbolic set with the star, for which the QS's and QU's are all positive, then this is an epsilon GPO. This is a true orbit, but with these scales, it satisfies these four conditions above. Okay, and you are right, the difficulty is how can we pass from this originally or like orbit, true orbit epsilon GPO to a not orbit, but still an epsilon GPO. Well, before that, let me just convince you that whenever you have an edge, the graph transforms are properly defined. I already told you why, because those recursive relations, they tell us that if you start with an almost horizontal graph and you pre-iterate, you go over the new stable window here at X, and vice versa for the almost vertical graphs. So the difference now is that almost horizontal graphs, you need stronger assumptions on the properties of the functions that you consider. So you see, almost horizontal graphs, they are defined only at the scale PS. And saying that they are almost horizontal, now we require strong assumptions on the zeroth position and zeroth derivative. And the assumption is related to the window parameters PS and PU. So the smaller the windows of the epsilon double chart, the closer f of 0 has to be to 0 for you to consider these almost horizontal graphs. So in some sense, for places in which it is very hard for you to see the hyperbolicity going on at the stable direction, you have to consider only graphs which are really, really, really almost horizontal. Because bad hyperbolicity means that you have to diminish these parameters, and then you have to consider f of 0 very, very small. Okay? The same thing for f prime of 0, and this condition was already contained in our previous lecture. So you see, it's much more complicated to define the space of almost horizontal graphs. We have to control these graphs much more precisely, exactly because at places with bad stable hyperbolicity, you might lose control of things if you do not require these strong assumptions. Well, you define the unstable, the almost vertical graphs in a similar way, and then you have the stable graph transform taking an almost horizontal graph at W and sending to an almost horizontal graph at V, and the same thing for the unstable graph transform, taking an almost vertical graph at V and sending to an almost vertical graph at W. And well, once we had graph transforms, the conclusion here as well is that these assumptions, they are strong enough to guarantee that these two guys are contractions, then we can compose many contractions and define, as we defined in the context of uniform hyperbolicity, stable invariant manifolds for these pseudo orbits, this generalized notion of pseudo orbits. The stable one, what do? We go far in the future, consider any almost horizontal graph, and then pull it back to the zero double chart, which is V0. Take the limit, this thing converges, and it will be the stable manifold of this epsilon generalized pseudo orbit. Same thing for the unstable, you go far in the past, and then you push it to the 0th position, and then you take the limit, and you get the unstable manifold of this epsilon generalized pseudo orbit. And these guys, they are genuine passing invariant manifolds. Of course, they are not invariant manifolds of the zero of the center of this chart, but they are invariant manifolds of any of the points they contain. Okay? So the idea here was that with this notion of edge, we can also define invariant manifolds for this loose notion of generalized pseudo orbits. Okay. And then we have again the same shadowing lemma, which tells us that to each epsilon generalized pseudo orbit, you have a single point that is shadowed by it. The single point is going to be the intersection of the stable and unstable manifolds of the pseudo orbit. So here I have drawn it in the different scales. So the unstable manifold will be drawn in the scale of PU. So it is an almost vertical curve with size more or less of the order PU. And the stable is an almost horizontal with size more or less of size PS. And you see, I require that these two guys are very, at the 0th position, they are very close to 0 with respect, let me come back here, to the infimum of these parameters. So that an unstable and almost vertical always intersects an almost horizontal. If I only require the almost horizontal to be smaller than PS and the almost vertical to be smaller than PU, then you could have a situation in which you had something like very tiny here and very big here that did not intersect. Okay? But if you require both objects to be very close to 0 with respect to the minimum of the parameters, then they will intersect. And the intersection will be this unique point in which I will say that it is being shadowed by the pseudo orbit. What does it mean? It means that its trajectory is falling inside the images of the passing charts with respect to the minimum of the parameters as well. Exactly because this intersection will also be very close to 0. Okay? So even though stable and unstable graphs are defined in windows of size PS and PU, the requirement on how horizontal and how vertical they are with respect to the minimum of PS and PU in order to intersect them. And now we get to the coarse graining. So the coarse graining is the tool, is the machinery that allows us to pass from these uncountably many orbits that we have in the set to a countable family of double charts for which the epsilon generalized pseudo orbits that they create, that they are associated to, shadow everything in the set. So this is a kind of a discretization argument that allows us to go from original orbits to pseudo orbits that still shadow everything that we want. In the uniformly hyperbolic situation, we did this just by taking a sufficiently dense subset of the manifold. Now, as Marisa pointed out, as Lucas pointed out, the sole definition of edge is much more complicated and harder to hold. So how can we do that? Well, the idea is to get all x's in this set and to look at all hyperbolicity parameters that they define. These 6 guys. And in some sense, to pass to a dense subset with respect to these hyperbolicity parameters. So what do I mean? I mean that for every x in this guy, I want to find a nearby y that has a nearby c of y, a nearby capital Q of y, small qs, and small qu. So now instead of only approximating x, which was enough for the uniformly hyperbolic context, I want to pass to a dense or sufficiently dense subset with respect to all of these parameters as well. Okay, and now because I'm allowing any non-uniform hyperbolicity to hold, in the sense that these guys here can be arbitrarily large, then I will actually consider a dense subset of points that approximate all of these guys. But fortunately, we want to consider this dense subset, and we will, as a countable subset. So the goal here is to pass from this uncountable set that is associated to all of these parameters and obtain a countable dense subset of it. So how can you pass from uncountable to countable and dense? Well, I believe we have a famous theorem in analysis, which is Lindelof's theorem, which is exactly allow you to get countable dense subsets. And Lindelof's theorem requires boundedness, pre-compactness. So in some sense, we have to use somehow pre-compactness here in order to be able to pass to a countable dense subset. How do we do? Well, we enlist everything that we want to control. So to every point x, we consider this tuple gamma of x, which is underline x. Underline x is just the position of x, its preimage, and its image. Underline c is just the 3 matrices C, also at these positions, at x, at f-1 of x, and at f of x. And the underline q is just the value of q at x. Why do I enlist all of these guys? Because in some sense, I want to pass from an original trajectory that is going from f-1x to f of x to some approximation of it. So I not only have to control the values at x, but also of the neighbors of x under the dynamics of f of x and f-1 of x, in order to guarantee that these approximations here will actually be edges. Okay? So in some sense, I want to consider all of these tuples and obtain a countable dense subset of it. Well, this belongs to the manifold, this belongs to the manifold, this belongs to the manifold is compact. So this varies inside a compact space. Everything is good. We could directly pass to a countable dense subset. This is bounded by, for instance, by 1. So this belongs also to a compact neighborhood of R. So we could also pass to a countable dense subset. But this is not. For matrices to belong to a bounded set, their norms and their inverse norms have to be bounded. And the inverse norms of these guys can be huge, because what C is doing is getting 2 vectors which are perpendicular and sending two vectors which might be making a very small angle. So the reverse direction, you would be getting two almost indistinguishable vectors and opening them to an angle of 90 degrees. So this means that the norm of these inverse matrices can be arbitrarily big. So these guys do not belong to a bounded subset of matrices. So what do we do to control? Well, we divide the space into subsets in which these guys are bounded. So for each choice of parameters L-1, L0, and L1, we look only at the gamma axis for which the inverse norm, the norms of the inverse of these guys are between e to the Li and e to the Li plus 1. And now these guys, they are bounded because both the norm of C and of C inverse are bounded, X are bounded, and Q is bounded. So these guys, they have countable dense subsets. And now we are done because the space of all tuples that we wanted to approximate is the disjoint union of these Y sub L's. Each Y sub L is pre-compact, so it has a dense countable subset. So if you consider the union of these dense countable subsets as L varies, you obtain a dense countable family of these objects. And using the dense countable family of these objects, and now again is a matter of faith, we are able to construct countably many double charts that are enough for our purposes. If you want, I can tell you exactly where it is contained in the survey, this construction, or either I can do it in the next lecture if you are interested in. But the main idea here is exactly to pass to a pre-compact set in order to obtain a countable dense subset. And then the conclusion is this theorem here. For the fixed epsilon, you can find a countable family of these objects. They are defined by the countable dense subset of the gamma axis above, in which these two properties hold. First of all, you have this discreteness property, which plays a key role in the construction in the future. It tells us that for every parameter t, the number of double charts that you selected, for which these two parameters are both bigger than t, the scales are both bigger than t, is finite. So recall that if you fix a parameter t, having these two PS and PU bigger than t is associated to passing sets. So in some sense, this discreteness property is telling us that to cover passing sets, we need only finitely many double charts. This in some sense is related to the original question of Ali. Ali said, why not getting the union of horseshoes? Here, in some sense, it's exactly what we are doing, because to each passing set, we have finitely many double charts. And then we get the union of them. So this is the discreteness property. And the sufficiency property is exactly telling us that all orbits that we are interested in are shadowed by pseudo orbits generated by this alphabet of charts. So you construct abstractly this family of countable double charts. It gives rise to a graph because you look to each edges from each double chart. You can go to another double chart. Then you have the paths on the graph. To each path on the graph, you have a shadowed point. So the sufficiency is saying that as you look at the shadowed points, you get all of the points in this set here. Okay. Ali, Is it clear, more clear now? In some sense,
yes,
that your
Yuri,
question.
thank you. So the hard work here in this theorem is on the sufficiency, in fact. Am I right? You should prove that it is sufficient, in fact.
Yeah, to get discreteness is easier. If you got the empty set, if you got the empty set of countable charts, you would get discreteness. So it's easy.
Exactly.
So the difficulty is sufficiency.
Okay, exactly.
Yeah. Okay.
And how do we explain for us sometime about sufficiency, or we should read it?
It's up to you. But basically, what you need to do is that you get these points of this dense countable subset, and from each of them you have the psi QSX, QUX. So you just have to allow this QS and QU to change a little bit, to vary a little bit. And if you have an original trajectory, you look at the Qs they define, so you will be able to find an X0 which approximates the Q of X, an X1 which approximates the Q of F of X, an X2 which approximates the Q of F2 of X, and so on. Okay? So this is the idea. This is very interesting because this new result about uniqueness of measures of maximal entropy, the authors, Buzicro, Vizier, and Sarig, are all the time analyzing things in compact regions, like truly hyperbolic sets. So this, from the symbolic point of view, they are related to this condition here, PS and PU bigger than T.
I was going to ask, can we guarantee that the bounded degree, or bounded degree, no, finite degree on this graph everywhere?
Exactly, we can.
Okay.
Yeah.
So,
yeah. So
what is the parameter controlling this this degree?
I think it's related to this, because you show, yeah, if you have an edge coming from this guy to another guy, then the minimum between, let me put like this, the minimum of PS, PU over QS and QU is close to 1.
Okay.
Yeah.
Great. Good. Thanks.
So it is a graph that has bounded degree everywhere. It's not finite degree, like in the sense that uniformly bounded. Okay. Yeah. This is actually one of the difficulties that I encountered when I did the construction for non-invertible systems, or the one-dimensional ones. I was not able to get one of the bounded degrees. I was able to get bounded outgoing degree, but not bounded ingoing degree. Well, later I was able, with Hermeson Araújo and Maurício Poletti, to bypass this. And the reason was that I thought that in the non-uniformly expanding, which you only see positively Lyapunov exponents, you could only work with one of the parameters, which is the QU. But then this made it complicated to get this bounded degree. So our idea was, even if you are non-uniformly expanding, also use the QS. So then we were able to get bounded again. But coming back to the discussion here, using this result of Sarig, which I call coarse graining, I think he also calls it, we can do as we did in the uniformly hyperbolic situation. We have now paths on a graph, left shift, and the coding map given by the shadowing, which is pi. To each epsilon generalized pseudo orbit, we associate a single point in the manifold. Okay. So now we come to the next input, which I call improvement lemma. So what is the improvement lemma? Well, the goal to motivate the improvement lemma is the following. The final coding that we want needs to be finite to 1. So we have, as I told you, to solve an inverse problem. So if I have this equality, if I know that V is shadowing X, I want, in some sense, to relate the hyperbolicity parameters of the charts of V to the hyperbolicity parameters of the shadowed point X. And the improvement lemma allows us to do that. The first natural question would be, for example, how can you compare the angles of the unstable directions of X with the angles of the invariant directions at X0? Well, analyzing the angles is easy. Why? Because the shadowed point, if you look at R2, it is defined as the intersection of an almost horizontal graph with an almost vertical graph. So the angle between these two objects is almost 90 degrees, as is the angle of the coordinate axis at X0. And if you apply the passing chart to pass from R2 to the original manifold, the distortion that you have is not that big, in a way that the angle at X0, the 90-degree angle, is going to go to this angle here, and the almost 90-degree will go to almost the same that you get at X0. So in some sense, the strong assumption that we required on these almost parallel graphs guarantees to us that after applying the passing chart, the angle that you have in the stable and unstable direction at X are very close to the angle that you have in the stable and unstable direction at the center of the chart. Okay? But a much more difficult question would be, for example, to understand why the S parameter is finite. I know that the S parameter at X0 is finite because X0 is in the non-uniformly hyperbolic set. But why is it finite for the shadowed point? I could have a nearby point with a rate of hyperbolicity slightly different from the rate of hyperbolicity of X0, to which S of X0 is finite, but S of X is infinite. This could happen. And here, it is very important to assume that the V that we consider is in this recurrent subset. Because for, sigma, the recurrent subset in the symbolic point of view. Because for the recurrent guys, we can guarantee that the shadowed point has finite S and U parameters. And the way we do this is exactly by using the improvement lemma. So what is the improvement lemma? Okay, so here's the problem, how to compare Sx and Sx0. And the improvement lemma is, if the ratio between the S parameters, so in some sense, you are comparing how good the hyperbolicity at f of x is with the hyperbolicity at x1 is in the stable direction. So if this guy is big, after you apply the graph transform, or the f minus 1, and you come back to x and to x0, then this ratio becomes smaller. More specifically, if you get a threshold of how big it is, so you fix some square root of epsilon, and if this ratio is of this order, e to the minus plus or minus square root of epsilon, then certainly S of x over S of x0 becomes inside a smaller interval. It is of the order now of psi minus this number, which is a positive number. So if this was the interval, let's say, of size 1/10 to 10, after you apply the dynamics f minus 1, the quotient between the S parameters will go to a smaller interval, let's say 1/5, 5, exactly because the psi diminishes to psi minus this. And why is this good? Because if you know that in the far future, you see a same double chart infinitely often, then as you try to understand S of x over S of x0 at the 0th position, you could do it starting with the S parameters, the ratio of the S parameters at this position, and then apply this improvement lemma going back to the 0th position. And then you will see one single improvement if you go from here to here. The single improvement is at least of the order q of y to the beta over 4. But if you do this a little bit further in the future, for instance, in the second occurrence of this passing chart, then you would see at least two improvements. One, as you come from here to the previous iterate, and then you come, you see some improvements, but they might not be big. Then you come to pass to the same passing chart that you were in the beginning. Then you apply it one more time. Then you see the same improvement again. Then you come back with improvements that you don't know how to control. And then you come here to the 0th position. So if you start with the improvement lemma from the second occurrence of this same passing chart, as you go back to 0, you see two improvements. If you do it from the third occurrence of the passing chart, you see 3 improvements. So you see many, many improvements as long as you are in this threshold. So the conclusion is that the improvement plan, together with the recurrence in the future, allows us to go over many improvements and then guarantee that the S parameter at the 0th position of x is very close to the S parameter of x0. So we, as a consequence, get that the S parameter at x is finite, and we also get that this finite value is very close to S of x0. So using this, we can obtain as a corollary that every coded point, if the coding sequence is recurrent, then the coded point is indeed in this non-uniformly hyperbolic sharp subset. I told you that Sarig proved this. More or less, his ideas in dimension 2 actually proved the reverse inclusion. But the reverse inclusion for higher dimensions was only proved by Benovadier. Okay? So I think this is a good point to ask if you understood what is the improvement lemma and how do I use the improvement lemma in order to obtain this corollary, because this is a main point in the proof.
Yuri, repeat again the improvement lemma, please.
Improvement lemma says that if this ratio is big, then it improves after applying f minus 1.
One iterate before, and you come back.
And the improvement is related to how good the hyperbolicity is at the center of the chart.
Mm-hmm.
So if you are seeing the same chart, the same x0, then every time you pass through this chart, you improve this amount.
And this is just the calculation, the definition of S of x or something more. How do you prove this improvement lemma?
Oh, that's nice. Why? Because this is the usual philosophy that along the stable direction, f minus 1 expands it. So if it expands it, it improves the regularity. It gets something that was very curved, and then it becomes less curved.
Mm-hmm.
Okay. Mm-hmm. Quantitatively, how is this obtained? You relate the S of x with the S of f of x. it is like 2 plus a constant times the original one. And the same thing for x0, more or less. So if you calculate this ratio with respect to this ratio, then you see an improvement in these ratios. So if this ratio is k, and if it's bigger than 1, much bigger than 1, then the new ratio is basically this, which is strictly smaller than k. Okay? So this is just saying that the fraction that you get, numerator and denominator become bigger. They are more or less of the same ratio, but they become bigger. So it's like 2020 over 2021 is much closer to 1 than 4 over 5.
Exactly.
Yeah. Okay. But philosophically, it is this. And this is somewhat used also in these approaches of anisotropic spaces. They make a direct use of the property that along stable directions, applying the inverse dynamics to improve the regularity, as well as along the unstable, if you apply it forward, you also do improve it. Okay. So if you see improvements, and if you see many definite improvements on the way that you pull things back to 0, then you have bounded ratio at the 0th position. This is a crucial step in the proof, right? Okay, because it's not clear at all that the S parameters at the shadowed point should be finite. You could have nearby points for which they are nearby to points on which the Lyapunov exponents are strictly greater than chi and smaller than minus chi, but for which the shadowing is not strong enough to control the Lyapunov exponent of the shadowed point. So you have some sort of semi-continuity here. And I believe this is, in some sense, the origin of this new work of this triple Buzikov, and Sarig, in which they analyze the lack of continuity of Lyapunov exponents. Okay.
Do the same thing happens to you?
The same thing happens to you, but you, if you have a ratio at the position -1, which is big, if you apply it forward, it improves.
That's why we need that condition on sigma
On the past as well.
Okay.
Exactly, because to control you at the 0th position, you should go in the past, see the same passing chart, and then iterate it forward to the 0th position. Yeah, good. So finally, we arrive at the 5th ingredient, which is the inverse theorem, which allows us to control everything that we wanted. So what does it say? It says that if you get an epsilon GPO, as Marisa said, that is recurrent, you see the same symbol infinitely often in the future, and the same symbol infinitely often in the past. And if you look at the shadowed point, then the hyperbolicity properties of the epsilon GPO are related and almost the same as the hyperbolicity properties of the coded point. How? Position-wise, the center of the charts are close to the nth iterate of the shadowed point. This is direct. The second one we already discussed with that picture. The angle at xn is very close to the angle at the shadowed nth iterate of the shadowed point. The third one is what we get from the improvement lemma. So the S parameter of the center of the chart is very close to the S parameter of f and of x, and the same thing for the U parameter. And using the recurrence properties that PSN have and that QSFN have, this guy allows us to actually prove that the window parameters are also very much related. So in the coarse graining, we kind of approximated these guys to shadow everything that we wanted. Now we are getting the reverse direction. We are saying that if we are shadowing a point with a recurrent sequence, then the only way that we can do is by choosing these parameters of the double passing charts very close to the parameters of the shadowed point. And this is an inverse theorem exactly because if you give me X, then all of these are automatically defined. Then the inverse theorem is saying that V is basically defined as well, because the parameters of V have to be almost defined. Okay? So this is telling us something about the inverse, the fibers of the coding map, the inverse image of X. This is the fifth main ingredient that is necessary to prove the theorem. Why? Well, let's do it now. Let's implement the 3 steps in the proof that we did on the last lecture now in this context of non-uniform hyperbolicity.
Wait, Yuri, sorry.
Yeah, please.
But you have not proved that the fiber is finite yet, isn't it?
No,
Okay.
no. And it will not be. Recall that from pi is usually infinite to 1.
Mm-hmm.
So to prove that the fiber is finite, first we need to do the refinement and get an actual Markov partition.
Okay, right.
This is what we do now. So that's why I said that these estimates, they play a crucial role to implement the Bowen-Sinai refinement. So what were the 3 steps that we did for the uniformly hyperbolic context? Well, we first did a coarse graining. In our case, was uniformly hyperbolic, was just considering a finite, sufficiently dense subset. Now, I consider the countable family of epsilon double charts that we got in the coarse graining. And then associated to it, we have the graph, whose vertices are the double charts and whose edges are defined by those 4 conditions that we introduced. So this gives rise to the symbolic space sigma, to which elements of it are exactly the epsilon generalized pseudo-orbits. So this completes first step in the construction. Second step, how do we get an infinite to 1 extension? I already did, but let me recast. We define pi just by shadowing, to which epsilon generalized pseudo-orbit, we get the intersection of the stable and unstable manifolds of this guy. So this defines a map pi from sigma to m. And we already know that the way we constructed the alphabet was in a way that the image of pi would be surjective onto this guy. Actually, the image of pi restricted only to recurrent sequences is surjective. Okay? And as we know, the other inclusion, we actually get an equality. The other inclusion was by means of the improvement lemma. So now we have this extra input in which we get the surjectivity and onto, we understand the image of pi restricted to this recurrent set precisely as being this set here. This is not true in the original paper of Sarig. Let me recall you, because the sets that he defines require the existence of Lyapunov exponents. We do not require, and not requiring, we are getting a bigger set that actually identifies the image. Well, this pi is a coding that defines an extension of our original map. So this commutativity relation remains true for the same reasons. And as before, pi is usually infinite to 1. So now we have to do the third step, which was the Bowen-Sinai refinement. In the uniformly hyperbolic context, it was very easy. Why? Because we got this cover, Z, which was a finite cover, and then we refined it. Now, we no longer have a finite cover because the alphabet here is countable. So we have countably many objects. Getting countably many objects, perhaps you might not be able to refine and still obtain countable. For example, if you get all intervals on R with rational endpoints, this is a countable family of intervals. But its refinement is not countable. Its refinement is that every atom is a point, is uncountable. So we need something else about this Z in order to refine and still get something countable. Well, now Z will actually be defined not directly as the image of the zeroth cylinder as it was before. We only look at the image of the zeroth cylinder of recurrent subsequences. Why? Because it's only for recurrent subsequences that we understand the variation, the parameters of the charts. So this introduction here makes this object to be much more complicated, for example, from a topological point of view, because this recurrent subsequence is neither open nor closed. So this image is usually not open nor closed. Before, we knew it was the image of a cylinder, which was a closed set. So from the topological point of view, we could understand Z of V in kind of a reasonable way. Now, since we have to intersect with this recurrent subset, we lose all control from the topological point of view.
Yeah, but Yuri, but still you have, these are rectangles, aren't they?
They are still rectangles in the notion of rectangles, exactly.
Mm-hmm. The boundaries are made of Bézier manifolds, Bézier stable and unstable manifolds.
Yes, not smoothly, because these guys, they are highly fractal. So they are like a bunch of points. The boundary is the intersection of a passing stable manifold with this the set itself. Yeah.
Like axiom A when you consider
exactly.
like Bowen.
Mm-hmm. Yeah. Yeah.
Okay.
Okay. So good. This guy is a cover of the set, but now is only countable. So how can we refine and still obtain countability? Then the main property that comes from the inverse theorem is that this Z is locally finite. What do I mean by a cover being locally finite? I mean that every point belongs only to finitely many rectangles. So although the cover is countable, when you fix a point and you look at the number of rectangles that do contain this point, this is finite. So locally, everything works as a finite cover, and a finite cover you can refine and still get finite. So as soon as we have local finiteness, we can apply the refinement and still get a countable cover. But just to convince you, why do we have local finiteness? Well, what do I mean by this? I mean, fix a point and see which rectangles can contain it. Assume that this rectangle is defined by this double chart. Then we know, because the sequence that is shadowing this guy is recurrent, that the parameters of this chart are close to the intrinsic parameters of the coded point. So then, PS and PU, the minimum between them is close to the minimum between QS and QU, which is Q. So whenever one rectangle contains X, it has to be in this subset of double charts of A. in which you have a lower bound for the minimum of the window parameters. Well, this set is a kind of a passing set. It's finite. So you have finitely many choices for the rectangle. Okay? So the discreteness assumption, together with the inverse theorem, which is what allows us to relate the parameters of the charts with the parameters of the shadowed point, is telling us that this cover is locally finite. And so we refine as before. And the conclusion is exactly the theorem that I stated in the middle of the talk, which is exactly of the existence of the Markov partition, which generates this coding, which is finite to 1 if you reduce the map only to the recurrent subsequences of your symbolic space. And furthermore, the image is exactly this subset here. Okay? So this completes the third lecture of the mini course. And now it's time for you to make more questions.
So just to be sure, the diagram you draw in the last slide is an upper bound for the degree, or is exactly the degree?
Diagram, which diagram? This one over here?
Yes, come back. No, come back one more slide.
This?
Yes, this is for this neighborhood.
Well, this not directly, because you mean the degree of this map pi, or of the graph?
Oh, of the graph.
Ah, of the graph. Well, if you get two guys, it's not because of this, but just because of the recurrence relations between an edge. If you have an edge, you have the relations between PS, PU, QS, and QU. So this implies that the minimum between PS and PU and QS and QU is close to, PS and PU over QS and QU is close to 1. So the edges that come out from the first chart, they go only to QS and QUs, which are approximately equal to PS and PU. And this space here is finite by the discreteness assumption. So let me write again. So if PS and PU is close to QS and QU, then the space of W for which you have an edge from V to W is contained in the space of double charts for which QS and QU is greater than or equal to PS and PU times a small value. And this later set is finite. Finite by discreteness. Okay?
Mm-hmm.
Yeah. So I believe you can ask questions to me, or you can ask questions to Omri as well, because Omri is here. So let's take advantage of his participation, of his kind participation.
Hi, Yuri.
Hi, Poya.
Will you explain then about the non-invertible case also in this mini course?
Yes, I will.
Okay.
I will. I hope to start it in the next lecture.
Yeah, thank you. Then the f-1 in the non-invertible case, you will you will consider along the branches.
Yes, I will consider the
Okay.
natural extension.
Thank you.
Yeah.
So Yuri,
Yes.
I have maybe a question about last class. So at the end of the class, someone rose the question about whether the elements of the Markov partition had fractal boundary, similar to what you were discussing a minute ago.
Yeah.
But in that situation, it could happen. It had nothing to do with the sigma sharp because we didn't have the sigma sharp in that situation, right?
Yes.
So,
it was a matter of codimension, actually.
Yeah, so I don't understand because we have this three-step construction in last class. So suppose we are dealing with one of those linear thorough automorphism with dimension at least 3. So this is expected to happen, but I don't see in these 3 steps where's the first place where, let's say, this fractal picture comes into
play. It comes into play when you get this object, which is a cylinder. It's naturally fractal, and you project it to the manifold. This guy lives in a symbolic space. It's like a contour set, and then you project it into the manifold.
Oh, so it's fractal because not all passages are allowed, something like this.
Yes.
Oh, okay. Thank you.
The reason about the boundaries that I mentioned is actually for Nosov and associated to, well, it's easier if you look at the construction of Adler and Weiss because it's more geometrical. So then you are able to understand nicer what would be the boundary. But with this construction, yes, it allows you to adapt the proof to this non-uniform hyperbolic situation, but it's more abstract. Then you get fractal objects and project, and then you lose control of what would be the image of these guys.
Okay, thanks.
Welcome. Any other question?
It's a silly question, I guess, and it's related to something someone asked earlier. But there is a way to choose a sharp C to consider these results. It is the topological entropy.
This guy?
Because if it's smaller, you are considering more measures.
Yes. And in some sense, considering more measures is better because then you can code with a single map all measures.
Yeah, but how can we take it sufficiently small but still being relevant to the map?
Okay,
it
so
has to be greater than the entropy.
Yes, if you are in dimension 2 and the topological entropy of F is H, then if you get a measure with topological entropy H, a measure of maximum entropy, ergodic, then you know by Ruelle's inequality. Let me put like this, just positive. Let me call H the entropy of the measure. Ruelle's inequality tells you that the Lyapunov exponents are greater than or equal to the entropy. So if you want to understand this entropy, you just need to fix a parameter chi smaller than H, than the entropy that you are interested. Because then chi is smaller than H, which is smaller than or equal to the Lyapunov exponents that you see. Then mu will be supported on NUH chi with this chi.
And any measure supported in the same set will have the same properties.
Yes, actually
we can forget the measure.
For all ergodic measures with entropy bigger than chi, they will be supported here. Any other question? There is no silly question, okay?
Yuri.
Yes.
How do you assure that you have the both Lyapunov exponent for the measure is different from 0? Why you don't have a big positive Lyapunov exponent and the other one is 0?
Well, here I am in the invertible situation, so I can apply Ruel's inequality also for f minus 1.
Okay.
So for f minus 1, so for f, you have the sum of the Lyapunov exponents for f greater than or equal to chi. So then you have at least one exponent greater than or equal to chi. But if you apply to f minus 1, the entropy is the same.
Okay.
So you have another Lyapunov exponent for f minus 1, which is greater than chi. This means that for f, you have a negative Lyapunov exponent.
Yeah. It's in the invertible case. Yeah, okay.
Yeah, exactly. I saw that Leandro and Ali would also wanted to make questions.
I'm just going to ask whether you are going to talking about the case where we have singularities in this situation.
You mean decay of correlations?
No. Singular sets. Sorry.
Yes. Next talk. Next talk. Yeah, I will start dealing with the flow, billiards, and perhaps non-invertible case. Okay, so I believe we can finish now. All the questions. So thank you all for coming to this third lecture. I'll see you in 2 days. Remember that tomorrow we have the beginning of the mini course of José Alves on SRB measures and Young towers. Okay. So see you all tomorrow and for my mini course in 2 days. Bye-bye.
Thank you. Bye-bye.
Thank you.